we tried to simulate these 5 examples in IT Lab on Wednesday, but if you haven't completed, that's fine. You can do it. You can continue next session, or anytime you're free, you can go to the IT Lab and continue your work. So we have all of these 5 examples in the eTabs. The example for 5 is a specific example I need to discuss in details. That's fine, but example 4.2 to 4.4 are normal examples. We will go through them. That's fine. Let's see what happens and how much we can cover today. So moving to example 4.2, it's a continuous beam with 3 supports and 2 external forces. And just to note that this is a symmetric structure. And if you remember from structure analysis from undergraduates, there are some methods that you can split a symmetric structure into half and analyze half of the structure, and the other half is just a mirror. You know, you have probably learned about this in the structure analysis in undergraduate modules, but you can imagine that those methods for splitting structures into a half were developed in such durations that the computers were not around, and these sort of methods were very valuable because you could decrease significantly the human efforts for solving or analyzing a structure. So it was quite something. But nowadays, when we want to simulate this with eTabs, for example, we really do not care about it because it doesn't make too much of a sense, because computer does everything, and it's just a difference of a couple of seconds. However, in reality, we don't have perfect symmetric structures in reality. So if you want to really design a structure, it's not perfectly symmetric in any case. So those methods just work for ideal cases like these, but not in reality. So anyway, we need to number the nodes. As you see, we have 5 nodes. Why 5 nodes? Because we need nodes 1, 3, 5, because we have supports there. We need to apply the supports conditions. We need them. And we need nodes 2 and 4 because we have external forces there. We need to have nodes there just to be able to apply those external forces into the problem. So that's why we have 5 nodes without considering the boundary conditions. We are working in beams area. So for each node, we have 2 degrees of freedoms, 1 vertical and 1 rotational. So 5 nodes times 2 means 10 degrees of freedom. In your coursework, you have, I don't know how many joints you did have, 6. So 12, you have 12. You need to work with 12 by 12 and eliminate some of them. So it's relatively as big as your coursework computation. So it's good to use Excel, because in Excel you can put these and you can whatever you want to do is easier to rather than a piece of paper. So for this purpose, we have 4 elements as well. So element number 1, number 2, number 3, number 4. Everything is identical for all the elements, because the element length, the element second module of elasticity, second moment of inertia, the module of elasticity, everything is the same for all elements. You can imagine the small stiffness matrix, which is 4 by 4, is the same for all of them, right? So we have one stiffness matrix for all of them. And when you have a 4 by 4 matrix for all of them, you need to assemble the big matrix. This is something that the author just skipped from because it's done in the previous example, and it's assumed that it's very easy to do. So for the big structure, we start from node 1 to node 5. For each node, this is for node 1, D1Y, Phi1. This is for node 2, this is for node 3, this is for node 4, and this is for node 5. So again, you can just write your hints here as well. This is a 10 by 10 matrix, and what we do is we transfer those small 4 by 4 matrices into the right places for all 4 elements. Start with element number 1, 2, 3, 4. So we have before continuing, I'm just want to emphasize that the 4 by 4 matrix is this one, as you see, right? In that example, we just substitute EI and L, right? It's a 4 by 4 matrix. Touching your question, assume that when we are having K1 and K2 for elements number 1 and 2, here we have EI over L3, which is a number, whatever it is. But because I is really a big number, E is a big number, this number will be something big. So it's a large number. So if it has, for example, assume that it has 28 here. They are not equal. All right. Assume it doesn't have. It's 28 EI over L3. It is just EI over L3, right? What you do is just bring this 28 into the matrix, multiply it with all the elements, and keep EI over L3 outside, right? It's not a big deal. See, the first is this one, the second is this one. Suppose that the first has alpha, the second has beta. Okay, they are totally different numbers. What we do? This is a question, right? Was this your question, right? If it's alpha, that's beta. They're totally different numbers, right? It's very simple, because you can say I can say like this. Alpha can be written like alpha times 1 divided by 1. Is it correct? 1 can be multiplied everything, right? Can I say this 1 divided by 1, which is obviously 1, can I say replace it by beta divided by beta? Is it still alpha? Alpha times beta divided by beta. It is still alpha, isn't it? I'm not adding anything. It's just, this is still alpha, isn't it? Is it? Isn't it? No, I want him to be sure. Is it beta alpha divided by beta? It is alpha. It is alpha, isn't it? Because you can eliminate these two. Beta divided by beta is 1, right? So beta divided by beta times alpha. I want the top one to be like the bottom one, to have the same identical value in front of the matrix. What to do? I will keep this beta out. I will bring this one in. I will keep one of the betas out, like I will say this is beta, and multiply whatever you have inside by the ratio of alpha b over beta. Does it make sense? I will bring alpha over beta in, multiply everything with it. I will keep beta there just to be like the bottom beta. Right? Whatever beta is, whatever alpha is, you can do this. This is just a very simple algebraic trick. It's like alpha times 1 is alpha. Okay. alpha times 1 is like alpha times beta divided by beta. Just keep beta there and bring alpha over beta in. So you will have beta, beta the same. So when you put everything into the big matrix, you know that beta can be outside the matrix, and you will work with the smaller values of numbers. So it's easier, right? Does it make sense? So what we have done here is just to put the small matrices into the right places, and we will get 10 by 10 matrix, which is for the whole structure. And then we need to eliminate the degrees of freedoms corresponding to those boundary conditions, which are obviously which one of them? This is 0. This is 0 because of supporting number 1, node number 1. Node number 3, this one is 0, but phi3 is not 0. It can rotate. However, for the symmetricity here, the phi3 is 0 because I know that the deflection should be symmetric, and as you see in the dashed line, the deflection is in a way that the phi3 will be 0. But this is a specific situation because of the external forces. If you eliminate one of the external forces, you will have phi3 non-zero. But for the initial, for the boundary condition, phi3 is free to move, but it doesn't move because of the external forces. That's another story. Also, phi5, d5y and phi5 are 0 because of fixed support at node number 5. So altogether, 5 of them will be eliminated. So you need to eliminate row 1, column 1, row 2, column 2, and row 5, column 5, and 9, 9, 10, 10. 5 of them will be remain for you to deal with like this. So in joint number 2, number 3, and number 4, you will have some unknown deformations and rotations. And here is a 5 by 5 matrix. And here you have your own external forces. The external forces are like, for example, here you have d2y and phi2. So here you have f2y equal to 10,000, and m2 is 0. If you had something like this, m2 wouldn't be 0. An external moment applied on node 2, right? You don't have such an external force there, so it's 0. And also, this is 0 because you don't have something like this here. If you had some external moment on node 3, m3 would be that one. And in node 4, you have this one 10,000, and m4 is 0. If you had something like this as well on node 4, it would be m4 there, non-zero, right? And generally, you can have a normal force on any node or an external moment on that, right? So the normal forces go to the F places, and external forces go to the M places in the left-hand side vector, which are a combination of external forces and support reactions here. But when you eliminate everything, it's just external forces, because when you eliminate those rows and columns, you're eliminating the support reaction in the left-hand side. So what we need to do here is inverse this 5 by 5 matrix and multiply it by this vector to come up with the unknown deformations on the right-hand side. However, the author of the book has used some symmetric situation here just to know, okay, I know those phis are 0 because of the symmetricity, and then try to break it down from 5 by 5 to 2 by 2 and solve this one. I don't. It's totally fine if you want to follow this, but I recommend just to try to inverse it by either Excel or MATLAB, and you will come up with these two numbers and these three numbers. Three of them will be 0, and d2y is equal to d4y, which are both equal to minus 0.048 inch. So the problem is solved, the unknown deformations are here, and the other parameters can be easily calculated based on the known calculated deformations. Any question here? So you can try to calculate the support reactions. How you do that? When you have the deformations, how you calculate the support reactions? Who is volunteer to answer? We have the unknown deformations. We want to calculate the support reactions. Hmm? Hmm? They are equal to 0, but here, no. That's for controlling your calculation, not for here for calculating the support reactions. So you haven't touched your coursework, have you? What? That's correct, yes. You probably have touched something. This was the big matrix, wasn't it? Let me clear up. The whole thing was arranged to solve something, eliminate boundary conditions, external forces. The whole story was arranged to come up with unknown deformations in the right-hand side of your equation. Some of these are already 0 because of the boundary conditions, and some of the others are already calculated based on these stories about inversion, multiplication, whatever it is, structure analysis. The core knowledge of this method is this inversion and multiplication to come up with these, right? These, when you do this, you have these 5 unknown deformations. Deformation means translational and rotational, both of them. So here, 5 of these 10 were 0, and the other 5 are now determined, calculated in the next slide. So you have all 10, don't you? So if you have all 10, this is known. This is a 10 by 10 matrix, known. Everything is known there. It's L, E, I, whatever. You have this 10 by 1 as a known vector in the right-hand side. You can simply multiply this 10 by 10 by this 10 by 1 vector, and the result will be a 10 by 1 vector. Always when you multiply A by B matrix by something like B by C matrix, these two should be the same. Otherwise, you cannot multiply. This is the first or second session. When you multiply two matrices, this should be the same. Otherwise, you cannot. All right. A by B can be multiplied by something like B by C. And the result will be the dimension will be A by C. Always. AB, BC, EC. What? I don't know, to be honest, because I haven't done this, but I suspicious to the answer to say I don't know because of two reasons. Because Excel is so powerful, I doubt it cannot. Second of all, I am a MATLAB guy. I never do that in Excel. I just start MATLAB. I'm a MATLAB programmer, so I don't use Excel for these kind of stuff. So I don't know the answer, but maybe you need to check. We can check. That's a good question, maybe. But otherwise, it's not very difficult. It's just like many of them are zero, actually. So for example, when you want to multiply, you can multiply each row by each column manually and put it there. It's not very difficult. There are so many zeros playing there. So 10 by 10 multiplied by 10 by 1 will result in a 10 by 1 matrix, which should be equal to this one. The right-hand side is known. The left-hand side is whatever I asked you. I asked you how you can calculate the support reaction. Support reactions are 5 of these 10. 5, the other 5 are the external forces. Here you have 10 numbers. 5 of them are external forces. 5 of them are here. Come with me. Wake up. 10 numbers here. 5 of them are external forces. The other 5 are what? Moment. Wake up. Please, wake up. Close your eyes. Open your eyes. Open your eyes. Get your coffee. There are 10 numbers here. 5 of them are external forces like F2Y. This is 10,000. All right. This is external forces. This is external forces. This is external force. This is external force. Exactly these 5 are external forces. They can be a number or zero. Some of them are 10,000. Some of them are zero because we don't have any moment there. My question is, 5 of these are, what are these reds? I just said 2 seconds ago. Come from the back of the class. What are these 5? Huh? Loud, please. Loud, please. Support force. External. Loud. External forces. The whole class. Quiet. External forces. Don't be shy. External forces. External forces. What are the other one? Support reactions. Don't be shy. Support reactions. So the left-hand side is a combination of external forces, which are known as zero, and support reactions, which are unknown, but will be known, you can calculate them, when you have those right-hand side unknown information, which is the core knowledge that converts whatever you are doing, right? Be precise, what are you doing? You have a vector in the left-hand side, a combination of external forces and support reactions. You have another vector in the right-hand side, which is what? The right-hand side. The right-hand side. Deformation. Some of them are unknown, some of them are known because of the supports. We know some of them are zero, right? But we do something, eliminate, reverse, calculate those right hand side, my left and right hand. Those right hand sides, and then we come back and calculate the reference. Right? This is the whole process. Doesn't matter you're working with bar element or truss structure or frame or whatever it is. The process is the same. You assemble your whole stiffness matrix, you deal with it, you come up with unknown deformations. Then with the unknown deformation in your hand, you can calculate whatever else you need, including support reactions, internal forces, or whatever, or internal stresses, for example. So here we calculated the unknown deformations, and here these are the results if you multiply that 10 by 10 matrix by 10 by 1 vector. And if you want to further go to calculate the internal forces in each element, you can use this one, which is the small stiffness matrix. In the first stage, you assemble this one and put these into the big matrix, right? For each element, you have this 4 by 4 matrix. So this is the first stage in each problem. You have the individual matrix for each element. So this 4 by 4 matrix can be used here to multiply by the corresponding deformation to come up with the internal forces for each element. So this is for element number 1, which connects node number 1 to node number 2. That's why you can see these are for node internal forces for node number 1, 2. These are deformations for node number 1, 2. So again, touching your other question, if another element is like 2 to 3, for example, this is 2 to 3, element number 2. Okay, this should be 2, 3, 2, 3. If you say, okay, I say the element number 2 connects 2 to 3, 2 is I, 3 is J, right? If you say no, I say 3 is I, 2 is J. When you come up here, you should not say delta 2, delta 3. You should say delta 3, delta 2. Right? The order is like this. Always here, when you come up here, the first one is I, the second one is J. Whatever your I and your J are. If you say, okay, the other one is I, okay, put that first here. Whatever I you choose. I say, okay, 2 is I, 3 is J. So here I have delta 2, delta 3. If you say, no, I is 3, J is 2, here when you get here, you should say delta 3, delta 2, F3, F2. The first one is I, the second one is J. All right? Shall we go for a short break and come back? For those who are still asleep, grab some water, coffee, or stretch your leg, grab some fresh air to wake up. Please come back in 10 minutes, okay? I'll fix it. Uh-huh.
Translation.
What's the question?
By doing e-test.
Uh-huh. You should close everything. because it's truss structure, it doesn't make a difference. But no, you should. The correct answer is you should close translational XYZ, get 1, 2, 3, or XYZ. The rotations should be free, but if you close the rotations as well, it doesn't change your solutions because, you know, we have hinges here, and because we have hinges, there is no, I mean, that if you close the rotations, because you have hinge, this element can rotate. It doesn't make a difference. You can close all of it. The vertical should be free. It's roller in vertical. So whatever, if translation along Y should be free, yes. Yes, yeah. Everything is restrained, but the vertical, yeah. Yes, yeah.
And for things,
Free, they are free. But because you are doing 2D, tell me what's your X and Y? What's your coordination system now? Is it X and Y? Write it down there. Okay, with this X and Y, for these, everything is free but translational Z, because it's out of plane, and rotational X and Y, because you only have, you can have rotation Z. Okay, you can have Z. Rotation X and Y are closed. However, this doesn't make sense, doesn't make a difference here because it's a truss, but it makes sense is if it's frame structure.
so I give support or something here. So I'm gonna assign restraint support here.
Yes, you should assign restraint here, like translational Z should be ticked and rotational X and Y should be ticked. It's a support, but it doesn't, it's support vertical to your plane of work. And it doesn't mean because it's a support, it will eliminate something in your stiffness matrix. It doesn't. Okay. You still have three degrees of freedoms here. 1, 2, and 3.
And here also the same.
Yes, 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 the same. Yes, the same, yeah.
The next direction. So we want to create the grid data using edit grids to something because the distance.
Yeah, you can have different grids. We had it in one of the examples. So if you press edit grid, you can add any sort of grid you like, or you can modify them. Like the first one is this, the second one is they should not be always the same. Right?
The next direction is 3.
Yes, you need 3 here, 2 there. Yeah.
And only the story number is 1.
If you work in, yeah, it can be 1. Yeah, because yeah, if you work in any plane, yes, it can be 1.
And story height should be
Yeah, it can be done. But in that case, if you're working with ETABS, when you're okay, you say a story is this one, you're working into XZ coordination system, not XY. That's the point. Okay, I told these like this, that when you simulate this in ETABS and you work in XZ, so don't mix it up with this. X means like this, Y means like this. So there you will have XZ plane probably.
Free to move in the Y
Yeah,
direction.
yeah,
We'd have to just say it's free to move in the Z direction.
yeah,
So
absolutely. You should just understand the concept. This is a roller support can move in this direction. Whatever this direction means, just take a look there, which direction it means.
Then here the same situation. Translation Y should be free.
No, why? Because this is why this is there.
That should be.
Yes, that's my point. I say, look, coordination system, when you change the coordination system, you should not mix up because this is a roller support. It means that this can move in this direction. Here, when you say X, Y, I say, okay, it is free in Y direction. When you say in ETABS, I have Z, okay, this should be Z direction. Both say this is vertically free to move. All right, depends on what kind of coordination system you're using.
That's this. And
Yeah.
the
Where?
story height and bottom story height as 1.71.
Yeah, that's when you have more than one story. So when you have one story, both of them are the same. Yeah. You're welcome. Yeah.
This owner support against the set allows the movement in Z direction, but what I did it like this in the system. This is the new support.
Yes.
So the translations all are fixed and the locations are fixed.
Yes and no, because for the truss structure, it doesn't make a difference, but to be precise, if it's not a truss, translation of, what are these? Is it? It is X,
Z and X.
X and Z. Okay, X, translation of X, translation of Z is free, that's correct. X and Y are closed, that's correct. X and Y should be free, X and Z should be
Fixed.
fixed. Why? Because this is X, this is Z, this is Y.
We will control this.
Y is free. But X means this one, this is closed, this is closed, but this is free. Right? Y should be free, those two should be fixed.
And this.
With this one, the same, but this one, of translation is Z is also.
The rotation about Y.
The rotation about Y is free.
So we exported the files, the files from trustee here.
You want to open it on your mobile?
No, not in the system.
Versions are the same.
That's one correct word.
Try to import it.
Yeah, included.
Does it work?
ETABS 19.
Are you sure it's ETABS 19 point something? Are they exactly the same? Try it again, probably.
No. Last year I had this, I didn't have the same thing, but if I did something on the 2022 version,
Yeah.
it would
that
go
makes
to
sense.
19,
Yeah. If you're working with 2022, yeah, you cannot, even in that case, if you import it, it would.
No, it was.
But for this kind of problem, bring the file. At some point we can do it together. Right?
Just make the changes today about this. And we
Yeah.
check.
Because this probably, there is some, if you repeated it, it will solve, probably you, I don't know, something is missing in the email, or something, it's just Windows errors. It should work.
So in this case, if the file doesn't open the submission, so it's better. I think it's better to produce the final results after the deformation in the app. And take a screenshot and put it in the PDF, so that you got to know that we did the analysis.
Yeah. That's totally fine, but still we want to solve this problem. It should not be. Okay.
I wanted to verify. So, okay, with the actual structure itself, it's easier to just break it into different segments, such as just triangles as it is, and then just work from there based on what we've gone over in class, right? The truss, because I've noticed, let's say there's the truss system. surely I could work on it like it's the triangle itself as opposed to just the whole thing directly, right? Okay, that's fine. I just want to clarify that. And
Work like this. If every individual element stiffness matrix, then the big matrix, then like the
Okay.
example.
that's fine. And the theoretical, so obviously our hand calculations,
Uh-huh.
does the MATLAB's calculation come into that? So if I went to MATLAB's and also did the direct stiffness matrix through there, yeah, that's fine. Okay, that's fine. Yeah, because I didn't know whether or not I should add that to the computational or if I should add that to my theory. But I guess I'll add that as a verification for my theory.
That's fine, but you should tell in your report what are
No,
you
no, no,
doing.
yeah. I'll just say like, okay, the MATLAB's used as a verification method. Yeah, that's fine. All right, thank you.
Come here and I'll fix it for you. Who has the problem with the registration?
I did the registration, but it's showing in the online. It's not thick here.
It's a, now it's a, I
Yeah,
updated. it.
part of the. Thanks. Sir.
That's,
Thank you.
you're welcome. I'm coming. This one starts. No. So this should be multiplied by 1,000, so it's like 0.41. This is 0.8. 2 times difference. Oh, that's a mistake. Yeah, there is a mistake. It's just 2 times. It's 100%. Take your course in index. I will add you today or Monday. Just right, you don't have to So we move to example 4.3, which has a difference with the previous examples, like having a spring connected to node number 3. So we have 3 nodes and 2 elements. If you hadn't have the spring, it was just a normal example like the previous ones. And because you have number 1, 2, 3 nodes, you have 6 degrees of freedoms, right? Node number 1, 2, 3. You have 2 degrees of freedom for each node. So 3 nodes all together times 2 means 6 degrees of freedoms, right? Do you remember what we used to do when we had a spring? When we had a spring, we have these 2 degrees of freedoms or internal forces. In the bar, the first topic was bar elements we covered, remember? We had 2 degrees of freedoms in parallel to the lengths of the element, right? For example, you can name this 3 and this 4. This is I, this is J. The node number 3 at the top of your spring is exactly the end of the beam number 2, which connects nodes 2 to 3. So because they are welded together, they are connected together, they move together in vertical direction, right? That's why I'm naming this node number 3 as this node number 3 the same, because they are connecting together. The top of your spring is connected to the end of the beam number 2. That's why the if you want to let me clear off. If you want to name the degrees of freedoms, it's like this. This is delta 1y. This is phi1. This is delta 2y. This is phi2. This is delta 3y. This is phi3, right? These are those 6 degrees of freedoms we are talking about. These 6 are unknown deformations in the right-hand side. Okay? The spring connects node 4 to 3, and I can say this is d3y or delta 3y, and this is delta 4y. This is I, this is J. Okay? Delta 3y is common between the top of a spring and the right-hand side of the beam, but delta 4y is something new, right? So it means that we had 6 degrees of freedoms. We have delta 4y because of the bottom of spring. And it means that we have technically 7 degrees of freedoms. And the whole matrix is 7 by 7 instead of 6 by 6 because of having this spring, right? And you know, when we say this is the spring, the K for the spring is K, whatever constant is, 1, 0, 1, minus 1, minus 1, 1, right? You have the stiffness matrix. Whatever you used to do, just repeat that. If you didn't have the spring, you surely were going with these 6, but now you have d4y, and what happens here is your stiffness matrix for the spring, which is this 2 by 2, stands for d4y, d3y, d4y, d3y. So it should go to these places. When you have your 6 by 6, the 6 by 6 matrix is clear how to assemble, isn't it? Because you have two elements. Okay, you have two individual 4 by 4 matrix for the beam elements. You put them in the right place. But after that, the spring comes into the calculation. So the question is, we had here, we had K 1 minus 1 minus 1, 1. It is only K. Why I see KL3 over EI into the matrix? Why is that? Any idea? Think a bit. The question is, anyone, but you can't tell me what is my own question. Yeah, boy, you know why he knows? Because it was some sort of discussion at the big lecture. Because he had gone to start face this question to the procedure. Asked this today in the morning. I addressed it. Then when I asked this question from everybody, I'm sure that we same question. He is settled already, so he knows what I'm. But for those that doesn't have any idea what my question was, the problem is that they don't have a mutual language with it. They don't know what kind of hell I'm talking about. Need to have the same terminology with each other. Technical. Believe me, if you don't keep up with the I'm originally Persian. I think Persian here. I'm what I'm saying. I'm Persian. It is identically the same if you don't study before you come here. If I speak in English, it doesn't make any difference compared with if I speak in Persian. Both cases you don't understand it. So why would you do that? You should have some backgrounds. The list I have, I don't know, about 65 students, right? But IT be less than 30 should come. But what's your good to have 30 on board? It means that half of the class don't give enough engagement. So we are in some sort of end of class structure, shortly moving frames, which are taken down cases. So still we are in the week for 7 out of 12. For the Esther. Really, the last alerts, last warnings for those who missed too much of the time in the first half of the. So please, please, please. All of these wire and repeat stuff like that. Just to inform you, just to remind you that we need to have a mutual technical understanding. It's not possible if you don't spend time out of the lectures. You should spend enough time to study the lectures, the exercises, IT labs, think about your shortcomings, be able to settle the final. Otherwise, it doesn't happen. The science still has not discovered any ampule injection either. Could happen at some point, maybe, but Elon Musk or Benson, stuff like that. Maybe they will discover some injection that we can only get the full 500. That's it. We don't need glasses. Take a pill, just fine. No, I don't want it. They're just small things. But just before we get to that point, the future probably is not out. We need to do these practices. There is no other way. At least I am not aware. There is not any other way than science, engineering, rather than practicing, studying, learning, and stuff like that. I've heard of any sort of. So, please, we are approaching the end of the semester. Take your time to keep up with the lectures. So, the individual stiffness matrix is like this: EI over L3 times something. For example, the first element is 12 EI over L cubic, right? Can you keep this in your mind? This is the first one, okay? Let's go to our example. What is this? Exactly, 12 EI over L3, okay? Multiply this here, what you will get? 12, or I will bring it here, 12 EI over L3 plus K. Yeah. In other words, let's make it simpler. In other words, I had a matrix seven by seven. I have a matrix 7 by 7, D1Y, D1, D2Y, D2, D3Y, D3, and D4Y. The same here, D1Y, V1, V2Y, V2, V3Y, V3, and D4Y. I have two 4x4 matrices I need to fill into this, all right? Those small 4x4 matrices are like EI over L3, the first one is 12, and so on, as we just discussed a few minutes ago. All right? So for example, the first one is 12 EI over L3 is for all of them. When you feel this part of the matrix, everything is coming from those small 4x4 matrices, which both of them have EI over L3 at the back, in front of the matrix, right? But I have another matrix for this spring, which says K 1 minus 1 minus 1, 1. And when I come to this point, I want to put the first element of this here. It's D4Y, D3Y, D4Y, D3Y. So the first element, which is 1 times K, should go to 2. D4Y is the column, D4Y here. This should go here. Okay, K should go there. Okay, that cell should have K. But if I straightforward put K there, it means that we have this one. This further will be multiplied there and will make it something else, not K. I should put something there considering this multiplication should produce K. So I put K L3 over EI. That when multiplied with the EI over L3 will produce K. I need K there, not something else. In another way, in another language, can we say when we have K 1 minus 1 minus 1, 1, can we say K is like this, K multiplied by 1 divided by 1? Again, I'm touching that question. Can I say it's like K, I put 1 over 1 like L3 over EI, L3 over EI. I put 2 times L3 over EI, L3 over EI. So they will go away and still we are 1 over 1. Okay. I bring this L3 over EI into the matrix and I keep the other one outside the matrix. The result will be K EI, or sorry, I will bring K inside as well. The result will be EI over L3. Inside, I will have L3K EI minus L3K EI minus L3K EI L3K EI. Now, the back of this matrix is exactly the back of this matrix. And you can simply put whatever you want into the big matrix, which is L3K over EI, right? Is it clear or not? Is it clear, right? So I'm just saying it's 1 over 1. You can put whatever you like for 1 divided by 1. All right? So having a stiffness, having a spring makes your problem having 1 more degrees of freedoms. Instead of 6 by 6, you have 7 by 7. And some of the K will influence into the big matrix, right? Still, we will eliminate this column and this row because this D4Y is restrained. The bottom of a spring is restrained. So the only top of a spring is open. And the only term that contributes to the solution is this one. And only this K will contribute to the solution. Whatever K is, if it's small or big, will contribute to adding something to that 12 to make it more stiff. Physically, it is a spring at the end of the beam. The more stiffness it has, the more difficult it will be to push it down. So if you increase K, it will decrease D3Y for sure, because you're pushing number 3 down with whatever, 50 kilonewton. The more stiffness you have, the less D3Y you will get. It's harder to push it down, right? So what we have done here, that this is the whole matrix, and after elimination, how many you should eliminate? You should eliminate 2 of you need to eliminate 2 degrees of freedoms here, 1 here, and 1 here. Altogether, you need to eliminate 4 degrees of freedoms, right? D1Y, Phi1, D2Y, and D4Y. Which ones are free to move? Phi2 is free to move. D3Y, Phi3 are free to move, right? So 3 degrees of freedoms are free to move. That's why after elimination, you will get a 3 by 3 matrix, and these are your unknown deformations. These are external forces. P is 50 kilonewton. Yeah. And if you calculate, inverse this matrix and multiply it by the left-hand side external force vector, you will come up with unknown deformations like these 3 values. It is calculated parametrically. However, it's okay if you want to assume some numbers. Yeah, we have numbers here. You can skip the parameters and from the beginning use the actual numbers, just to not to bother yourself with the parameters. And anyway, you should get this one. However, we have the solution in ETABS as well, pretty much close to these. And a question? Any questions so far? So furthermore, if you use this big matrix, now you have these. Okay, when you have these, you can multiply it by this. You will come up with these, which give you the support reactions. So you will have all of the support reactions and external forces here. And for example, when you calculate the support reactions, this is 69.9. You can put it like this because you know the beam element was like this. The convention was like this. So if this is like this and I come up with minus 69.9, I can put it down to up minus 69.9, or vice versa with positive 69.9. I come up with this number for M1. So the convention is counterclockwise. You can make it negative and put the number positive. If any sort of force 10 kilonewton, it is identical to say minus 10 kilonewton, and just change the direction. It is identical to say, okay, minus 20 kilonewton meter, this is moment. It should be, for example, kilonewton meter. It is positive 20 kilonewton meter if you change the direction. It's always the case. So always the convention is like this. The normal forces from bottom to top, and the moments or deformations, rotations are counterclockwise. Okay. So here, what you can do to check your calculations is when you come up with this sort of, this is called free diagram of your structure. You have all the forces on your structure, including the external forces. So this is external force, and the others are reactions. These are reactions. So for this free diagram of your structure, the equilibrium equations should be satisfied, which means summation of x along y should be 0. It means that this 69 point something and this one and this one and this one, these 4 should be 0, including the directions. So for example, you should say to just to write it down, if I would say 116.4 plus 3.5 minus 50 minus 69.9 should be 0. Right? I just took these two positive and these two negative. And summation of m should be 0 against any point you like. You can have it like in the left for against point number 1, 2, or 3. But usually I prefer to write this equation for the point that more normal forces are crossing, because the more normal forces crosses a point, this is more simpler to write it down, because those don't contribute to the question, because to the equation, because they are 0, distance are 0. So I write it to the point number 3 because 2 of the forces are crossing point number 3. They will be out of the game. So it would be 116.4 times 3 meters. It is clockwise. I'll put it minus, plus, this is counterclockwise, plus 69.9 times 6 meter, and minus 69.7 should be 0. I don't calculate it, but you can give it a shot. They should be 0. It will be 0. So if they are 0, it means that you didn't have any error in your calculation. The equilibrium equations are satisfied based on these obtained results. Is it possible, question, is it possible to have some errors, come up with some numbers here, equilibrium equations show that we are 0, but we actually have done some errors? Is it possible? Can it be okay? Right, if not right. If it is 0, this is the statement. Why? Why there cannot be another set of numbers that satisfy this? Structuring. That's again true, but a little further, I would say the solutions for equilibrium equations are unique. You only have one set of solutions for reaction. You cannot have two sets of solutions for your subtle reaction. You have two sets of solutions for unknown equation. The solution of your problem is unique. It means that there is only and only one set of solution for these equations. That's what. If you have more than a set of solution for your equilibrium equation, it definitely means that your structure is unstable. Definitely your structure has a problem. There are two ways. Or your structure is unstable, or you have done something wrong in your calculation. There is not any other option to explore. So example 4.4 does not have anything really rather than having an external moment on node 2. Nothing. It's really like the example 4.2 today we went through, but in that example you had some support here. It doesn't matter. The only difference is you have 20 kilonewton meter here, and as I mentioned, when you assemble your stiffness matrix, we don't have it here. You can just repeat example 4.2 just to assemble the stiffness matrix, and when you come up, for example, here you have 3 nodes, 1, 2, 3. So altogether 6 degrees of freedoms, which mean delta 1y, T1, delta 2y, P2, delta 3y, P3. And the whole matrix would be 6 by 6, right? And when you assemble the 6 by 6 matrix in the right-hand side, you have the unknown deformations like delta 1y, phi1, delta 2y, phi2, delta 3y, phi3. And in the left-hand side, you have f1y, phi1, f2y, phi2, and f3y, phi3. In the right-hand side, the delta 1y 0, phi1 0 because I have a support. Delta 3y 0, phi3 are 0 because I have another support. Only delta 2y and phi2 are free to move in the node, in the middle node, in the node number 2, right? In the left-hand side, these two, f2y and phi, oh, sorry, this is not phi2, this is m2, m1 and m3. F2y and M2 can have numbers. F2y is minus 10 kilonewton, and F2, this is minus 10 kilonewton, and M2 is 20 kilonewton, positive 20 kilonewton, because it's counterclockwise. Right? The other 4, these 2 and these 2 will be eliminated, and they are support reactions. Can be calculated later on. Okay? The remaining, after you have 6 by 6, you will eliminate 4 of them. You will remain by, you will be left by 2 by 2. So in the 2 by 2, you have these 2 minus 10, 20, and these 2 unknowns, and a 2 by 2 matrix from the middle one. And just solve it. Do it at home. There is no new thing. This example, like the previous ones. The only example we didn't touch is number 4.5, the last example, which I'll leave for the next session. It has something to touch because it has a story behind it. I already have provided an Excel file on the Moodle that is accessible. That Excel file is for example number 4.5. It will talk about shear deformation. It's an important thing to learn. We need time to explore that option. And that's something for the next session. But before that, please, how much I should please? Know what I answer. I don't bother you more. Just the final question. Which lecture room is your size? Then you go 206. You meet there, Mariana is here. There. Any question? Okay. Otherwise, good luck and see you next week.